Strong acids and weak acids. A strong acid is one that ionizes completely in solution. A weak acid does not ionize completely. It only ionizes a little bit. If we just look at names and formulas, hydrochloric acid, HCl, hydrofluoric acid, HF, they seem to be similar, right? Chlorine and fluorine are sisters on the periodic table, and here they are hanging out with hydrogen, and so they appear similar. But there's a very significant difference between them. HCl is a strong acid, HF is a weak acid. Why? How? That's beyond the scope of this class. Strong acids ionize completely. They are strong electrolytes. A strong electrolyte will conduct electricity well. It forms a lot of ions. You put HCl into water, all of the molecules separate into ions. They form ions. There are no HCl molecules left. So if you have a 1 mole per liter HCl solution, it's going to have a hydrogen ion or a hydronium ion concentration of 1 molar. And when we put the brackets around a chemical formula, it means the molar concentration of whatever that is. So this means the concentration in moles per liter of hydronium ions. When we put HCl in water, the HCl acts as the acid, the water acts as the base. I don't know why I can't point down there, it's disturbing. Yeah, it is messed up. H3O plus is formed in chloride. Any questions? Because all of the HCl reacts, whatever the concentration of this was that we added, that's the concentration of the hydronium ion that we're going to get. This is a conductivity apparatus. Here we've got a light bulb with wires going off to the wall socket. But instead of a continuous wire here, there are 2 electrodes, and we're sticking them in water. If we touched those together, the light bulb would light up. But they're not touching, and the pure water does not conduct electricity, so nothing happens with the light bulb. If you add HCl to this water, it ionizes and forms chloride ions and hydronium ions that can carry the electric current, and the light bulb lights up. A strong acid is a strong electrolyte. It makes the light bulb glow strongly. These are the 6 strong acids. There's only 6 of them. Hydrochloric, hydrobromic, hydroiodic.
Do we need to know those?
You should know these. You can pass the class without knowing them, but it's good to know them. Give it a shot. So HCl, HBr, HI, those are the halides, right? Those are fluorine's big sisters. HF is not on here. She's the little sister. She's going to break the pattern. So these are strong acids, and then there's nitric acid, perchloric acid, and sulfuric acid. Most of these are monoprotic, meaning they only have 1 ionizable hydrogen, but sulfuric acid is called a diprotic. 2 protons, 2 hydrogen ions that can be donated. A weak acid, like HF, does not ionize completely. Here we've got a double-headed arrow, meaning this goes both ways. When we looked at HCl, this arrow only goes in one direction, only goes to the right, because it separates and that's it. It stays separated. With HF, this reaction can go both ways. When we put HF in water, some of it ionizes, but a lot of it does not. And so what's actually in the water is more HF molecules than fluoride ions and hydronium ions. There are some. It is an acid, but it only ionizes a little bit. That makes it a weak electrolyte. It's a poor conductor of electricity. We look at the light bulb, and the glow from this is weak. It's a weak electrolyte. There are ions here, but not as many. There are fewer ions, and so fewer electrons get transferred across, and the light bulb glows more dimly. These are some weak acids. The way you know it's a weak acid is it's not one of the strong acids. If it's not one of the six, it's a weak acid.
In the reaction with the, like the one you just showed, would fluorine be considered the base, or would that not be?
You mean in this reaction?
Yeah.
So this is an acid, and this would be the fluoride would be the conjugate base.
Okay, but not a base itself. Would it be a base itself? Like in the
Well, when you turn the equation around and look at it going the other way, this would be the base and this would be the acid. Many of the weak acids are carboxylic acids. They're naturally occurring. Things like acetic acid, formic acid. That's the acid that ants have in them, those California fire ants that sting so bad. They're injecting you with formic acid. It hurts. So this is a conceptual question. Which of these pictures is representing a weak acid? So remember, a strong acid separates completely into ions, and a weak acid does not. You'll have intact molecules. So which one of these beakers? C. C has, this is formic acid, it has intact molecules, and then it's got hydronium ions, and it also has the formate ions. Here, there's hydronium ion and there's nitrate ion, but there's no HNO3. There's no HNO3 molecules. And here we've got hydronium ions and iodide ions, and there's no intact molecules. So the weak acid is beaker C. Without the labels on there, you'd have to sit there and stare at that for a long time to make sense of. You just stare? You don't need to sit and stare?
No, you can see because like those colors are all the same. Those colors are different, and those colors are very different. So it's obvious when you see.
Well, I'm glad it's obvious to you. It's not obvious to me. This one, the first two, there's only two kinds of particles.
Right.
And this one, there's three kinds.
But they're separated.
Yeah.
Those aren't.
Yeah, here you've got the separated ones and the unseparated ones. I'm not going to draw pictures for you on the exam, so don't worry about it too much. Okay, let's determine the hydronium ion concentration in each solution. So here we have 0.50 moles per liter HCHO2. The first thing we have to ask ourselves is it a strong acid or a weak acid? It's weak. If it's got carbon in it, it's going to be a weak acid. You could go look at the tables. This is a weak acid. So in a weak acid, let's draw the equation. So the weak acid, the HCHO2, we put it into water. It's going to act as an acid. It's going to donate a hydrogen ion to the water. So we're going to get H3O plus, and then we're going to look at, well, what's left after we remove that hydrogen and a positive charge. We've got CHO2 with a negative charge. And this is a weak acid, so this has a double-headed arrow. So this concentration, 0.50 moles per liter, we're taking 0.5 moles of this, putting into a liter of solution, but then some of this is going to react and form hydronium ion and formate ion. It's a weak acid, though it's not all going to form this. In a strong acid, all of this becomes hydronium ion. So can we actually calculate the concentration of hydronium? No, not with the knowledge that we have at this point. Can it be done by someone in Chem 1B? Yeah, but you need some more information. So all we can say is the hydronium ion concentration is going to be less than 0.5 because it's a weak acid. So the hydronium ion concentration will be less than 0.50. Some of it will ionize, but not all of it. And so, maybe half of it, maybe a fourth of it, but the hydronium ion concentration will be less. You okay with that? I'd prefer to actually just calculate the stupid number, but this is what the book does. How about this one? 1.25 molar high. Strong acid, right? So strong acid, when that gets mixed with water, ionizes completely. So we get the hydronium and iodide. It all does this. So for every one of these, I get one of those. So what's the hydronium ion concentration going to be? 1.25. It's the same, because it all ionizes. Okay? HF, strong acid or weak acid? It's weak acid. Just the little sister, she's weak. So because this only ionizes partially, what can we say about the hydronium ion concentration? It's just less than the concentration of the acid.
So we need that first off before you even draw it.
Yeah, you don't actually have to draw the equation. Oops, not equals, less than.
Would you have to draw them if there was ever a case where you didn't get like an even number of moles or whatever?
Well, the time when you really would want to consider the equation, at least in your head, is if you had a diprotic acid or a triprotic acid.
So then you have like
A two or three hydrogen ions. But it turns out sulfuric acid is a strong acid in its first hydrogen, but the second hydrogen coming off is weak. And so I won't give you any questions like that, because it'd be mean. And I am many things, but I am actually not mean. Sometimes I seem mean, but I'm not mean. Yes?
Like in the example for B, if the molar ratios were not 1-to-1 in the reaction, how would you then figure it out?
Okay, so let's make a hypothetical acid. So let's call this H2A. So if H2A was a strong acid with both of its hydrogens, it would use two water molecules. It would form two hydronium ions and A2 minus. So the hydronium concentration would be twice that of the starting. If you started with one molecule of H2A, you'd get two hydronium ions, because there's two hydrogens on this. And if you had 1 mole, you'd get 2 moles. And if you had 1.25 moles, you'd get 2.5 moles, because there's 2 of these for one of those. Turns out there aren't any strong acids like that.
Oh, so we'll only have to.
Yeah, you only do the ones.
Okay.
Strong bases are bases that completely dissociate in solution. So the metal hydroxides are strong bases. So these are all just metal hydroxides. The diprotic acids like H2SO4, it will lose one of its hydrogen ions and then it'll lose its second hydrogen ion. Bases don't do that because they're ionic compounds. They just dissolve into all their ions at once. So some of these, like strontium hydroxide, will give us 2 moles of hydroxide for every 1 mole of the base. We don't have a name though, like dibasic bases or anything. diprotic, but there's no corresponding name for the bases. So we put a strong base in water, and it completely separates into its ions, and it's a strong base. It'll conduct electricity and be a strong electrolyte. Weak bases are like weak acids. The one that you need to know about is ammonia. Ammonia is a weak base. It will react with water and accept a proton from water, but it only does that a little bit. And if you look at what's in the solution, it'll be a lot of ammonia molecules and some ammonium ions. Generically, we can write it as B for weak base plus water is going to give us BH plus OH minus. Here, this is the base holding the hydrogen ion, the proton. You put ammonia in water, you've got a lot of ammonia molecules and only a few ions. There's lots of weak bases. Common ones are organic amines. These, you can think of these as variations of ammonia. So here's ammonia, NH3, and it'll accept a hydrogen ion. Pyridine is, here's that nitrogen again, but it's got this other stuff stuck on it. But it's the nitrogen that acts as the base, and so the nitrogen takes that hydrogen ion. It's just got different stuff hanging off of it for these different ones. Bicarbonate ion, or the hydrogen carbonate ion, can act as a weak base. So hydrogen carbonate, let's think about this. So H2CO3, that's carbonic acid, right? So if that reacted with water, we get hydronium ion and HCO3 minus the hydrogen carbonate ion. This is the acid, this is the base. Conjugate acid, conjugate base. This conjugate base can accept a hydrogen ion. It could accept a hydrogen ion from water and make carbonic acid the conjugate acid. So sodium bicarbonate, baking soda, is a very useful thing. It can neutralize acids and it can neutralize bases. Okay, determining hydroxide ion concentrations. So, barium hydroxide, is it a strong base or a weak base? It's a strong base. It's a metal hydroxide. Bang, it's a strong base. Let's think about what happens with it, though. When you dissolve that in water, you get a barium ion, and how many hydroxide ions? 2. So the number of hydroxide ions is twice the number of the original units that you dissolved.
So 2 times 0.
So it's 2 times this. You can also think of this in more of a stoichiometric way. 0.055 moles of barium hydroxide per liter. And I'm going to get 2 moles of hydroxide for every 1 mole of barium hydroxide. I'm figuring if I can't talk and can't read, I probably can't do math in my head either, so I'm just going to use a calculator. 0.11 moles of hydroxide ion per liter. Or we'd say the hydroxide ion concentration equals 0.11 capital M. Okay?
Okay. For you separated it.
Mm-hmm.
I'm not really sure how you separated that.
Well, I was just looking at the 2 different ions.
Why does the OH still have 2?
Well, in front here,
Mm-hmm.
because I have 2 of them. So this is like a bicycle, where barium is the frame of the bicycle and the hydroxides are the wheels.
Yeah, but you took away the two and you took away barium, didn't you?
No, there's two wheels on this, and I take the bicycle apart, I have the frame and two wheels. So there's the frame and there's the two wheels. We can talk about that later if you'd like. What about B? Is this a strong base or a weak base?
Weak.
Weak base. It's not a metal hydroxide, this is a weak base. So the hydroxide ion concentration, is it going to be the same, more, less?
Less.
Less. Because it's only going to react with the water and form hydroxide ions a little bit. So the hydroxide ion concentration is just less than 1.05.
How do we know, like, there's no difference in moles for that one?
Well, the nitrogen can only pick up one hydrogen. And that has to do with its Lewis structure. I mean, if we look at ammonia, it's got two lone pairs on one lone pair on the nitrogen. And so that lone pair is what can bond with this hydrogen ion that doesn't have any electrons. After the nitrogen has picked up the one hydrogen ion, it can't take any more. It doesn't have another lone pair to share. Okay. Sodium hydroxide, strong base, weak base? Strong base. So you can write out an equation showing how it ionizes, or you can look at the formula. Just looking at the formula, you can see that there's two hydroxides in here. So I need to take this concentration and multiply by 2. Sodium hydroxide, it's 1-to-1. So in 1 mole of sodium hydroxide, there's only 1 mole of hydroxide. And so the hydroxide ion concentration is going to be equal to the overall concentration. Any questions?